GC optimization team at the NCI, and I'm going to be talking about some work that I've done to initially sort of scale up some coupled climate models to perform an initial assessment of the performance and to get on track to scale them up. So I'm going to focus on the GC3 seasonal prediction model. This is comprised of an atmosphere model, which is the unified model out of the Met Office, an ocean model, NEMO. Marshall did mention this previously, but I'm working with a later version. It's also coupled to a sea ice model out of Los Angeles called SICE, and we've got an IO server as well. This performs the IO for the ocean and ice models while those models continue to run. And this is normally run in 30-day blocks for 10 or more years, but for the purposes of this work, I've shrunk this down to a one-day model run. So that'll be representative of the full length of jobs and everything except for IO. So I'm going to be ignoring the IO server for the time being. So the atmosphere and the ocean, they're entirely separate things. They're separate solars, they run on separate grids, they're using separate decompositions. Not only that, but they're actually entirely separate applications. Normally, these things are run in a standalone, completely standalone, or as Marshall has coupled with an ice model. And this is known as MPMD operation, multiple process, multiple data, and it's not really how MPI was intended to operate. But it can do it, reluctantly, as I've discovered. So these submodels, they run on separate cores, they run simultaneously, and they have to exchange data between themselves periodically. And so we need some other piece of software that can exchange these fields and interpolate between the two different model grids. And this is called Oasis 3 MCT. So now even something as simple as scaling a model up becomes this at least five, possibly more dimensional problem, because we can choose how many processes we want in the north, south, and east-west directions for the atmosphere. We've got the same way we can decompose the ocean, which will most likely be a different decomposition. We have to worry about how many cores we want to devote for IO. We've also got to worry about things like hybrid parallelism. Both the atmosphere model and the ocean model support threaded operation at various efficiencies. And fortunately, in this case, the atmosphere and the ocean time steps are the same. So one time step involves both models by 20 minutes. But that isn't always the case. So there's this potential in other coupled models to have multiple timescales going as well. And an important factor is the submodels, the atmosphere and the ocean cannot proceed until the coupling is completed every time. So what this means is that we can't just say double the number of cores for the atmosphere and expect any improvement at all, because we may just be increasing the amount of time that it has to wait for the ocean to catch up. So we have to be able to quantify how well these things are balanced. And normally we've got a collection of profiling tools available to us at NCI, but these just don't work with MPMD operation. The usual one we go to, which is SCORE-P, which I believe a lot of Marshall's graphs that he just showed you were based on the output of SCORE-P. But when this is run in an MPMD style operation, it just hangs and dies and you can't get any data out of it at all. We've got a tool called Open Speed Shot, which is similar, except it will only profile one of the running applications and not all three of them at a time. And we do have access to Intel VTune, which works similar to Open Speed Shot, but because we're targeting a particular MPI distribution, Intel VTune only works with Intel MPI, and so it doesn't work with our chosen MPI distribution. We do have, the only thing I've managed to get working so far is IPM, which is a pure MPI profiler, and it does work, it works properly, but it lacks the detail we need to really diagnose how well balanced these things are. So this is the configuration that was handed to me at the start, and it's pretty clearly, I know enough about the about the unified model to know that it's not spending 70% of its time in communication when it's running standalone. So we can sort of, you can see that the sharp sort of cutoffs here on either side, and we've got 192 cores for the unified model, and the next 256 are running the ocean model, and then we've got 24 cores running the IO model. So we can tell from this and what we already know about the UM that it is a pretty unbalanced configuration. The atmosphere is going to be spending a long time waiting on the ocean. But something more subtle would be very difficult to spot. What we can get from IPM is a breakdown of the actual calls used by the models. But the trouble is that doesn't help because both the way that the models communicate between each other through the coupler and the way that the models actually exchange data between themselves uses the same pattern of calls. So we can't really, they use asynchronous send receives and an MPI wait all, which we can see is the red call here, and that's spending 2/3 of its time in that wait all. So there's really no way we can sort of determine exactly what's going on just through this profile alone. So at this point, MPMD profiling is kind of underdeveloped because it's not common at all. You don't really see a lot of MPMD applications running. So really all we've got is we have to insert some internal timing, but that should be sufficient to be able to balance the submodels and to test for efficient scaling. But to make sure that we're running efficiently, we have to be able to separate the cost of the coupling from the cost of the solvers. So there's a fair amount of local expertise in the UM and NEMO. So what we're really trying to find out here is how they interact with each other through the coupler. So when we think of coupling within one of the submodels, within the atmosphere or within the ocean, we can break it down into two components. The first of which is where if one of the models is running faster, the first component is where it needs to wait for the other model to catch up. And the second component is the actual exchange and the interpolation of data. So obviously, to balance the model, you need to eliminate that first component as much as possible. And so in order to do that properly, we need to be able to quantify the actual cost of the exchange and the interpolation. And to do that, we're going to intentionally run some quite unbalanced jobs. So this is the job from the IPM profile broken down by model time step. And so the blue on that graph is the actual time spent in the atmosphere solver. And the red is the time spent in coupling. And you see the coupling occurs every hour, every model hour, every 3 steps. And there's a quite sort of large coupling step here. This is actually 40 seconds that it's spent doing that initial coupling step. But so if we look at the ocean, this is the ocean model for the exact same one. They were running simultaneously in parallel. And we can see that the coupling barely makes up any of the runtime at all. So it ended up being about 150 milliseconds spent in coupling time for every model hour. So that's around 1% of the total runtime. And this is good news for us because what it means is that the scaling of the ocean within the coupled model is going to be dominated by the scaling of the standalone ocean model and not by any sort of crazy interactions with the coupler. So it makes it more of a known quantity. And so we can see that the UM is running a lot faster than NEMO, and the coupling is relatively inexpensive. So now we have to do the opposite. We've got to slow down the UM and speed up NEMO and get an idea of how much it costs to perform this operation in the unified model. So we've scaled up NEMO. We've just about doubled the core count in NEMO. We've got the time step down to about 2.2 seconds, which that's quite reasonable scaling. It's about the efficiency of just under 90%, I think, when doubling the cores. And of course, we've got these characteristic spikes of waiting for coupling. We know that the true cost of the exchange and the interpolation is about 150 milliseconds, but here we're seeing about 4 seconds. So we're definitely waiting on the atmosphere now. And the same story presents itself in the atmosphere. Now that the atmosphere isn't waiting for the ocean, the coupling is revealed to be quite inexpensive. About 1/3 of a second for every model hour, which is a bit more expensive than the ocean model at 3% of the total runtime, but it's still quite cheap. So we've done this, we've isolated the coupling time, and it's a relatively small portion of the runtime, which is quite positive. This means that the scaling of the entire coupled model is going to be dominated by the scaling of individual components and not by the interactions with the coupler. So next steps, we're going to scale this thing up as high as we can get it to run efficiently, which I think some runs that I did yesterday, it's going to be looking at 1,500, 2,000 cores. The entire model will be about the limit. And using this, then we balance the new, faster running decompositions. And then once that's done, we will still need some more information, so I do have to try and find